All right, welcome. In this explainer, we are diving deep into unsupervised learning and K-means clustering. If you've got an exam coming up on this topic, you are in exactly the right place. We're going to break down everything you need to know to really master these concepts.
Okay, so here's our game plan. We'll start with the big picture, what it means to learn from unlabeled data. Then we'll get our hands dirty with the K-means algorithm itself. After that, we'll see it in action in a hands-on lab with real retail data. And finally, we'll tie it all together with the key takeaways you absolutely need to know.
So, first things first, let's tackle a big question. What happens when your data doesn't come with, an answer key? How do you possibly find the patterns that are hiding right there under the surface?
And this, right here, is the absolute key idea. With unsupervised learning, we are not trying to predict some known outcome. Not at all. Instead, we're basically acting like detectives. We're telling the algorithm, hey, here's a massive pile of data. Go explore it and show me the natural structure. Show me the hidden groups inside.
Yeah, this slide just hits the nail on the head. Think about it this way. Supervised learning is all about prediction. You have the questions and the answers, and you're just training a model to learn the formula. But unsupervised learning, that is all about discovery. You only have the data, and your mission is to find the meaningful groups within it.
And trust me, this is not just some abstract theory. Unsupervised learning is the engine running behind the scenes in systems we use every single day. It's how your favorite streaming service groups you with similar viewers to recommend a movie. It's how your bank spots a strange transaction that might be fraud. And it's how news websites can automatically group thousands of articles by topic.
Okay, so now that we get the what and the why, let's dig into the how. We're going to focus on one of the most popular, most intuitive clustering algorithms out there, K-means. And I'm telling you, this is an absolute must-know for your exam.
The best way to think about it is like this. Imagine you just dumped a huge, messy pile of Lego bricks all over the floor. K-means is the little robot that comes in and automatically sorts them into different bins for you. A bin for the red bricks, one for blue, one for yellow. And that point in the very center of each bin, that's what we call the centroid.
The way K-means works is this really cool iterative process. It's kind of like a dance with two steps. First, it assigns every single data point to whichever cluster center is closest. Then, it updates those cluster centers by moving them to the average position of their new members. And it just keeps repeating this dance, assign, update, until the groups are totally stable.
Let's make this really concrete with a customer spending example. We've got data on how much customers spend and how often they visit. Our goal is to find the natural groups or segments hidden in this data. For this example, let's say we want to find two distinct segments.
Okay, step 1. The algorithm just randomly plops down two starting points. These are our initial centroids. Then, for every other customer in the dataset, it calculates the straight-line distance to each of those two centroids and assigns the customer to whichever one is closer. And just like that, we have our very first super rough draft of the clusters. Now for the magic. Once we have those initial groups, we find the true center of each one. The centroids literally move from their random starting places to the actual average spend and visit values of all the customers that were just assigned to them. They're moving to the center of mass of their new group.
And now we just rinse and repeat. We reassign every single customer to their closest new centroid. And guess what? Some customers might actually switch teams. Then we recalculate the centroids again. We keep this little dance going until the groups finally stabilize and no customers change clusters anymore. At that point, the algorithm has converged and we've found our final customer segments.
But hang on a second. How did we know to choose K equals 2? 2 customer segments. Why not 3 or 5 or even 10? This right here is one of the most critical decisions you have to make when you're using K-means.
Well, a really popular technique to help us decide is called the elbow method. What we do is run K-means multiple times with different values of K, say 2 clusters, then 3, then 4, and so on. We plot the results, and we're looking for the elbow in that graph. It's the point where adding another cluster just doesn't give us much of an improvement. That's our sweet spot.
All right, theory is fantastic, but let's see how this actually works in practice. We're going to walk through a lab scenario using a real online retail dataset to segment actual customer transactions. Now, for your exam, knowing this workflow is absolutely key. It's the standard playbook. You load the data, you clean it up, you select and prepare your features, you run the algorithm, and then, and this part is crucial, you evaluate and visualize your results so you can actually understand what you found.
So, since we don't have true labels to check our work, how do we know if our clusters are any good? Well, we use metrics like these. For your exam, here's a simple rule to remember. A high silhouette score is good, and a low Davies-Bolton index is good. They both tell us that we found tight, well-separated clusters.
And finally, the really fun part, we visualize. A scatter plot like this just brings the data to life. We can instantly see the groups the algorithm found. Maybe one cluster represents bulk buyers who purchase huge quantities at a low price, while another represents premium customers who buy single, high-priced items. The visualization is what tells the story.
All right, let's bring it all home. We'll wrap this up with a focused review of K-means pros and cons, and a final summary slide to make sure you are absolutely ready for your exam.
So the bottom line is this. K-means is awesome because it's fast, it's simple to understand, and it works really, really well when your data forms these nice spherical clusters. But it does have weaknesses. You have to tell it how many clusters to find beforehand, and it can really struggle with complex shapes or data that's full of noise and outliers.
Okay, if you are going to take a screenshot of one slide from this entire explainer, this is the one. This is your exam cheat sheet. It summarizes every key concept we've covered. It has the core definition, the algorithm's components, how to choose K, how to evaluate the results, and the full practical workflow. Know this, and you are going to be in great shape.
And this leaves us with one last important thought. K-means looks for these neat, round groups. But what about the real world, where data is often messy and complex? Think about intricate social networks or winding geographical patterns. Understanding the limits of this powerful tool is the first step toward choosing even better models for more complex data.